Alright, so let's begin by noting that the rocket and the photons form an isolated system. So the momentum of the system of the rocket and photons is conserved. Now let the speed of the rocket be v at time t. That means that the momentum of the rocket at time t is just its mass, which is big M, times v. So now let's consider a small time interval dt. So in that time interval, the number of photons being emitted by the engine is n lambda. So the number of photons being emitted is dt times n lambda. And the momentum of each of the photons is p lambda. So the total momentum of the photons that are being emitted by the engine in a time interval dt is dt times n lambda times p lambda. Now since momentum is conserved, the rocket must gain the same amount of momentum in the right direction. So that means that dp rocket, which is the momentum it gains from the photons being emitted, is equal to dt times n lambda times p lambda. Now, if we divide dp rocket by dt, make that p a little bit bigger, and take the limit as dt goes to 0, we get that dp rocket dt is equal to n lambda times p lambda. So this is part A. So now, notice that the momentum of the rocket is also given by big M times v, which means that dp rocket dt is just equal to d big M times v over dt. Now the mass of the rocket stays relatively constant, so we can treat M as a constant and factor it out of the derivative. So now we have big M times dv dt, and notice that dv dt is just the acceleration of the rocket in the x direction. So that's equal to big M times a of x. Now we can equate these two equations to get that big M times a of x is equal to n lambda times p lambda. So the acceleration of the rocket in the x direction is equal to n lambda p lambda all over big M. Now for the second part of the question, we're asked to find the velocity as a function of time. So using our kinematic equations, velocity at time t in the x direction is just the initial velocity plus the integral from 0 to t of the acceleration in the x direction dt. Now, we're given that initial velocity is 0, and we know what the acceleration is, so we have the integral from 0 to t of n lambda p lambda over big M dt. Now, n lambda and p lambda are constant as well as big M, so this whole term is constant, which means that the integral is just the constant times big T. Or not big T, but little t. So we've got n lambda p lambda over big M times t. So let's just write that again. So the final velocity at time t in the x direction is n lambda p lambda over big M times t.